So in part 2, we are going to discuss the specific non-parametric methods, which is a chi-square, using the chi-square statistics. Oh, and there are more you can see above. But this we start from the first one. It is common and very useful because it's intuitive. And so let's take a look at these questions. I'm pretty sure most of you, or I can even say all of you, have been wondering about these kind of questions and how to test it. So, for example, in the first question, you might wonder if the lottery numbers are evenly distributed, because sometimes the number seems skewed, like 999996 or something. Or maybe if you take some statistics, you look at a big set of past data on lottery numbers, you may see some numbers that appear more frequent than others. So you have to you want to know whether your hypothesis is true or not. Are they actually even distributed or not? And that's a fair question to ask. Second, how about what types of movie people prefer are different across different age groups? So that's another common question of, okay, we have a set of genres or categories. In this case, movies, like scary movies. Oh no, I mean horror movie, action, animation. And you want to know whether a particular age group prefers one type of movie over the others. And we can do that using the chi-square statistics, and then lastly we want to know whether a coffee machine. I'm sure most of you drink coffees. I do. Right? I'm not sure if the machine was dispensing approximately the same amount of coffee or not. So maybe the first time you get that much. Next you put a button and it gives you only like half of that, and then maybe next day you get slightly more than usual. And so maybe you can if you have time and you have tools, you can measure the volume of these cups of coffees and do the usual hypothesis testing. But if you don't care about the actual, you don't care about whether it's like half or twice or the ratio, you just want to know whether it's more or less. That's just a simple binary choices. Because that can be estimated using your own eyes without any tools at all. And so you can test that using the chi-square statistics and the hypothesis testing. Alright, so we can answer all these questions, but let's take a look at it one by one. Oh, let's take a look at math first. Right, so of course, since it is not normal, we don't assume any normal distribution, or maybe sometimes it's not even normal. Like for example, in the first case, it is A. Right? A is about the lottery numbers. So let's say there are 4 numbers, 4 choices A, B, C, D, and then I claim that the number of letters in the box are evenly distributed. So let's say there are 100 tickets in the box. So you should expect 25 tickets each, if they are indeed evenly distributed. But of course that's not the case sometimes. If the box is rigged or something, so that's not normal. And then the question is what kind of distribution it is. Is it gonna be the same curve, or is it gonna be like exponential that goes one way, or is it the curve that is skewed a little bit? The answer is of course it's one of the curve is gonna be skewed in this way. But the nice thing that allows us to do math is that these questions, I think all these 3 questions can be answered using variation of normal distribution. Variation of normal distribution. So for the normal distribution, we let z be the random variable, right? But that's just a single c, and we get this nice curve center at 0. But here we are going to use a variation of z, right? Remember how we can add 2 different normal 2 different random variables together. And for example, if I let x be the result of 6-sided dice, y be the result of 10-sided dice, then I can ask what is the I can define a new random variable that combines these two together, and that's gonna give you a different distribution. And this one is even, this one is even, but then when you add them up, it's gonna have sorry, gonna have kind of like a kind of a pyramid shape, right? Similarly, for this for the chi-square, we are using a version of normal distribution. What we do is we, as the name suggests, we square it. And so let's just look at one example. So if you square this curve, what is going to happen? Right. So let's use a blank here. So let's say we have a C there. It has a nice curve. And there's 0. So what if we set Z square? And so we have 0 there. So let's say let's take a look at this line. Let's say it's 1. Right, what is 1 square? 1 square is 1. So the height or the numbers that lie that are on this line is also going to be mapped on this line. Or you have to understand how the line number line transforms a bit. And so okay, let's say that's 2. And 2 is going to be mapped to what, to 4, because 2 squares 4, of course. And so you kind of it's as if you move that line over there. I should have made it the same height. And then you repeat the same thing for all numbers, not just integers, all numbers on this line. And so you kind of get this kind of curve, and it gets stretched out because we square the numbers. What about negative? When you have negative numbers, then you square the numbers. What you get is you get the positive numbers. So that means is the left portion of this curve is going to be kind of like lay on top of the first curve that we have. So that's C square. You stack together these two curves. Okay, so let's say you have 4 minus 1. Minus 1 is there. Minus 1 square is 1. Let me put the bracket back. Okay, so you these numbers, the values or the density of this number on the line is put on top of that line. Because we still have to preserve the total area of the curve to be 1. And we can move around like, as long as we don't scale. And we still have the same scale there, so the area is preserved. And similarly, if we have minus 2 there, right, minus 2 squares is 4, so you have put that line on top of the 4 value. Right, and so on and so forth. So yes, and since we only have to deal with 2 numbers, and this is the curve we have. Right, and then the final curve is just one curve. I don't have the 0 there. It's just one long curve. And you kind of increase the height of the right hand side by 2 and stretch it out. And so that's the source of this chi-square. If you study more math, if you do the math, this is necessary to understand how they got these numbers. But again, since it's just introductory, see how nice it is to manipulate from the variable or the thing we already know to make something new and interpret it in different ways. So that's how we get the chi-square. But that is just only one. See, like if it's just what C squared, then the world would be a better place. So what we have here, we have let's take a look at it. We have a bunch of Z. And so that's one curve. We add that curve, like think of it as one dice. Like you draw a die and you get a number under the curve of Z square. And then you add the value of that dice to another dice using the same curve. Then we have maybe 3, 4, 5, or 6 dice. That's number of dice is there. We have 10 dice, so we have all the values of all those 10 dice. And the result of the summation is exactly the chi-square. And the chi-square is going to have different shapes. Oh, don't worry about the details yet. Maybe pause and read if you want to. But another details we have to that is going to be needed is degree of freedom. And we discussed the concept of degree of freedom a little bit when we talk about the T distribution. And then we have to take into account of number of data or number of points. Here also we have to take into account number of data, but n is going to be different, so we going to discuss how to pick the value of n. And then you can go to, of course, the same website of, I forgot for the name of the author, but click on the green link if you have the file. Or if I don't forget it, I'm gonna put it under the clip. Right, so you put the degree of, if you go to the website, you get this like without a curve yet. If you type in the number into this new, I think, yeah, then it's gonna give you a curve. So if new is 9, in this case 9 is the degree of freedom, and you get this curve that look kind of like normal distribution, but kind of skewed to the right. And so the another thing that is necessary to see is that it starts at 0. And the reason why, because we square everything out, so we're not going to get a negative number. We have a nice curve. And we have, of course, the expected value, standard deviation, variance if you want to know all those numbers. And we're gonna use this soon, so you can like type, go to the link and just keep it for a while. Right, so for the motivation is, this is kind of blank. Right, the motivation is that we use chi-square distribution with iterative data. So we just count how many of people or how many of objects are in each category. And so here first we have these 4 columns. For this example, it's an edge group, but the formal word is categories. Categories. And the numbers don't matter. If you want to take that into account, then you have to use something different. But let's just say we are only concerned about the group is group A, B, C, and D, and they don't have to interact anyway. You can have melons, apples, grapes, oranges. They don't have to be from like least to most or smallest to largest. Just make it groups. And in the rows we have the number of. This is counting how many objects or how many people are in each group. Okay, categories. And here, yeah, we have 4 categories. We do a survey and we get 2 in the first group. The first age range, just 13 in the second age range, 10 in the third age range, and 3 in the fourth age range. So that's all we get from the survey. And interestingly, that's all we need for the chi-square test. We don't need any other assumption. We don't even need to know the numbers, as long as we know they are groups. Oh, we have to know as we have to have hypothesis. To test, right? Just the data and hypothesis about the data. Of course, this has to be before you do the survey. You can't just look at the survey and make up your mind to match the survey afterward. And the next thing, how we do the math, is going to be the math part. And so we have the formula here, and then some setup. So suppose that the frequency data, in this case the table, suppose it has k cells or k entries. We let the observed count. So that's the observation. That's the number you get from the sample. And let this observed count to be OI. So in this case, it's just these numbers. These are all. And then we have the expected count. And by expected, it means this is the expected count is coming from the hypothesis itself. And so suppose we know there are 4 age ranges. And we need to have some hypothesis. We have to make a guess on how the distribution will look like. And that is expressed as the expected count. So we have O and we have E. Yeah, the numbers in a different line. If you have O and you have E, then we can compute the chi-square test statistics, which is this formula. So what's that formula? Let's zoom it in. Right, so that's the summation. Right, so we take the sum of numbers. We have O, the observed, there. We have E, the expected, there. And what we are doing here is we take the difference. So this is the indication of how much different it is from the expected, from the hypothesis and the actual data. And we take the square because it is chi-square, and because positive numbers is easier to deal with. And then we divide it by the E. And so if you remember, just memorize that, then that's fine. That's all you want. But if you want to try to understand what this formula is saying, it's pretty much that straightforward. And so we take the sum because we have to take into account of all cells. If there are 2, 13, 10, 3. If there are 4 cells, then you need to take into account of all 4 cells. So that's the sum. Then we take the difference, right? Because we want to know how much differences there are from the observed and the expected. Let's say that's the observed. Then we have the, I should make it green. Nice. Oops. So that's the observed. And then we have the expected E. Suppose we expect to see 7 each. Oh, that's gonna be the number we use. Yeah, so this formula is measuring how much the difference are across the entries. Right? And for example, 2 and 7 is large. That's a large difference. We expect 7, but we only got 2. So of course, the number that is going to contribute to the final formula is it's going to be large as well. And 7 and 13. We expect 7, but we got 13, so the difference is 6. And that the difference is reflecting on that formula. And then we take square again because we need a positive number, and square is easier to work with than the absolute value. Right? The absolute value is also fine, but it's more difficult. And lastly, we have this interesting denominators EI. Why do we have to take into account of the expected count? Right? Because let's say we have, for example, let's say we only have 2 categories. Right, so let's say we expect to see 100 in the first column, and we expect to see 5 in the second column. And then we make a survey, ask people, and the result is in 99 prefer the first one and 6 prefer the second one. So if you look at just the absolute difference, the difference between the expected and the observed numbers are 1 in both cases. Right? But the first one and the second one are not the same one. Right? Because if you think about the ratio, and what matters is the ratio. If to drop from 100 to 99, right? But the difference is only 1% drops. Right? We expect 100 and the result is 99. So that's nothing. Right? Just 1% is and this is more likely to not be 100. It's not going to be 100 sharp. It's going to be plus and minus. And I think that is, let's say, as acceptable difference. On the other hand, if you expect 5 and you get 6, right, the difference is of 1 here is worth 20%. Alright, so in the first column is 1% loss, and in the second column is 20% gain. Okay, so that's huge, right? From 5 to 6 is 10%. Maybe it's even easier to see if you expect 1 and you see 2, and the difference is 100% gain. It doubles. And so the same ones are difference across the entries. So we have to not use just the reference, but we have to scale it by the factor of the quantity, in this case, the observed. So that's the origin of this formula. And let's see, one example of how to actually compute the chi-square. Just keep this formula in mind. Suppose that we have this table, which is the same table we just showed, right? And it has the number of students there, and then we have the expected numbers of students. And let's not let we are going to do the hypothesis testing next. But for now, let's just compute the chi-square. What that's all we have. And then compute the chi-square. Right, so the chi-square is gonna be the chi-square, and then you can write the formula first if you want to. It's the sum of since there are 4 columns, the 4 entries, so it's the sum of I. Oh, I think they use K, right? Oh yeah, no, right. 1 to 4. And then the observed minus expected square divided by expected. What are those things? Right, so we have this 2. Right, we have the numbers from the survey, so that's the observed. And then we have the expected number, which we need to establish before we do the survey. And so that's E. And so for the first column, right, we take the difference between O and E, so it's 2, and then minus 7, and then of course square divided by 7. That's the number 4 on the first column. And again, we are measuring the difference, and then we square to make it positive. Then we divide it by the expected count to scale it, so that everything is in the same scale. That's for the first column. So we can repeat that for the next column. Right. So for the next column, the expected, the observed, right, we see 13 students in this age group minus 7 from what we expect to see, square, and then divided by 7. And you can see the trend. We can just oops. Let's repeat that. Let me write that. Because next we have 10 minus 7 divided by 7, and lastly we have my head. We have 3 minus 7 divided by 7. So that's the chi-square. That's statistics. And you can do the math in your head or using a calculator. Let's do it in your head first, because it's not too hard. 2 minus 75 minus 5 minus 5 squared is 25. That's the first term. 13 minus 7 is 6. 6 squared is 26. Next is 10 minus 7 is 3. 3 squared is 9. And then we have 3 minus 7 is 4. 4 squared is 16. I need to move to the right a little bit. And then you add them up. I think the final answer is 86/7. And that's the answer for this example, the 86/7, which you can write down if you want to. It becomes 12.85. No, 12. 12. 5. No, 0.3. 0.2. 2x. And we are going to do just repeat the same thing over and over in the next session. But for now, that's the end of the second part. See you in the next part.